So thank you very much for the introduction and also for the invitation. I'm basically giving this talk now from Mainz because I'm at the ISE conference there. So it's actually my second talk today. So yeah, maybe I'm a little bit tired, but I'll give my best to introduce you on our modeling framework for electrochemistry based on continuum non-equilibrium thermodynamics. So first of all, we can ask, well, why do mathematicians actually care about this? Yeah? And here just a brief word about our institute. So the Weierstraß-Institut for Applied Analysis and Stochastics in Berlin is part of the Leibniz Association in Germany, so which is, beside Max Planck, one of the big pillars of fundamental research. We conduct project-oriented research in applied math and fundamental research on material modeling based on non-equilibrium thermodynamics. So electrochemistry is just one branch, but we have different groups dealing with all different aspects of PDEs and non-equilibrium thermodynamics. And our subgroup is more or less dedicated to electrochemical systems and charged interfaces. We have seen many application areas which deal with electrochemical systems, so from fundamental stuff to bioelectrochemical systems, batteries, corrosion. And we are part of the DFG Cluster of Excellence Math Plus. And our goal is always solving complex problems in science and technology with mathematical models and simulations. And of course, in order to do so, we need reliable mathematical models. And this is, let's say, my main research branch. They are the derivation of reliable models for electrochemical systems. So the central pillar question. One second, I have to get rid here of some annoying windows in between. So the goal, the first question you can ask in electrochemistry is what is happening at electrode-electrolyte interfaces. So you consider a single crystal metal electrode and some ultra pure electrolyte. You apply a voltage and you want to know what's going on in between. And this is our first step in this first lecture here, the development of a rigorous thermodynamically consistent model framework for liquid electrolyte and charged interfaces. And we need for this, of course, high fidelity and quantitatively reproducible electrochemical measurements in order to do some robust model validation. Oh, and by the way, of course, you can always interrupt me and ask every type and kind of question in between. Yeah? Just as a teaser, this is where we are already. So on the top, you can see a measurement of the so-called differential capacity as a function of electrostatic potential. This is the x-axis. And on the lower part, you can see what our model, in a sense, yields. Yeah? So we can really achieve a very broad qualitative and quantitative agreement with respect to applied voltage E and also with respect to salt concentration C without any artificial parameter variation. Yeah? And so this is kind of, let's say, the teaser for this. And once we are there, we can use these type of model frameworks in order to compute, for instance, current voltage relations for pseudocapacitance systems with partial charge transfer, even discuss solutions of mixtures, charge transfer reactions, multi-step reactions, and so on. So this is, let's say, what you can do with it. And in order to get there, I will try to guide you a little bit through the modeling procedure. So there were already some talks on DFT, which do really atomistically resolve every individual species. And what we are dealing with more is the so-called general field theory of coupled non-equilibrium thermoelectrodynamics for volumes and surfaces. So this goes back to groundbreaking work of Josef Meixner in the 40s already, and then it was pretty well developed by de Groot-Mazur, Ingo Müller in the 80s. I did myself my dissertation on this. And yeah, there's, of course, a lot of work in this regime. And this was just a brief selection. If you want to get more details about references, please just let me know or write me an email or via our chat system. So we consider here in the volume or the volume itself as a mixture of species densities So number of species divided by volume, where you send the volume to 0 in order to achieve what you would call a density. And these densities are all space and time dependent. And on the surface, you can have similar entities. So you have on surface, you can have surface densities, which are, for instance, adsorbates in electrochemical systems. They are also, again, space and time dependent. Of course, they do change their units. So in volumes, we have mole per cubic meters, for instance, and on surfaces, mole per square meters. And in order to close the set of balance equations you will see in a second, we need free energy densities and chemical potentials. This is where thermodynamics comes into play. So we state for every volumetric phase a free energy density in terms of this species densities. Here, for instance, N0 to NV. So you have NV species, for instance, in an electrolyte consisting of a solvent, some anions and cations, you would have 3 species. And by mu alpha, we denote the corresponding chemical potential, which is just the partial derivative of the free energy with respect to molar concentrations. There are also, if you would write here not the free energy density, but the free energy as a volume integral, then you would have here the Frichet derivative, but it's in principle the same idea in behind. On the surface, you can have a similar quantity, surface free energy, again expressed in terms of surface concentrations, and then quite similar, a surface chemical potential as its partial derivative with respect to the corresponding surface species density. And then in a rather general way, for every continuum volume and surface, you will have a set of balance equations. So for instance, in the volume, you would have for mass densities rho alpha, here the mass balance, the individual mass balances together with the mass balance of the total of total mass, and a quite similar thing you would have also on the surface. It's a little bit annoying that I don't see a pointer for myself. I have to figure out where I get this. I'm sorry for that. Yeah, so we have balance equations in the volume and on the surface. Then, in addition to that, you have a momentum balance, or in an unstationary state, this would be the Navier-Stokes equation. On the right-hand side, you have on the surface the jump of stress, which is proportional to surface tension. Then you have also an expression for how the electric field is jumping at interfaces proportional to surface charges. And then thermodynamics in the last row tells you how mass fluxes are related to gradients of chemical potentials, and on interfaces, how the flux onto or through an interface is dependent on differences in chemical potentials. So this is in essence, let's say, the general framework, if you want, which is in principle applicable to almost any type of continuum material where 2 volumes are divided by an arbitrary bended or curved surface. The first real big task in terms of material modeling is to derive chemical potential functions from a free energy density. And in order to do so, you have to state a free energy density, which has a lot of different type of contributions, from entropical contributions, mechanical contributions, some reference contributions of the pure substances, Debye-Hückel contributions, polarization, and so on. And the key idea is always that this is an additive, that the free energy density is additive based on these different components. And I want to give you some insights into of these free energy density contributions, the entropy of mixing, and the mechanical contribution, in order to derive, as I just said before, the chemical potential function, because this is, let's say, the heart of any type of continuum modeling. So I don't know how familiar you are, because I don't know the audience yet. I will be there in 3 weeks, but and to get known of you all a little bit more in detail. But for basic chemist students, what they normally learn about the entropy of mixing is that that you basically count the number of permutations you have in a mixture. So you can exchange an anion and a solvent molecule. You can exchange solvent molecules, and so on. And based on this idea of counting numbers, you get an expression for the so-called entropy of mixing. However, in real electrolytes, you will have something which is called the solvation effect. So every ion tends to agglomerate a certain amount of solvent molecules around its in a solvation shell, and by this you find that when you're counting entropically what exchanges are possible, you will find that you can exchange solvent molecules, you can exchange solvated ions, you can even exchange a solvated ion and a solvent molecule. But exchanging a solvent molecule and one from the solvation shell is not something which is an entropic permutation anymore. And if you do this mathematically sound and you assume that each ion bounds a certain amount kappa alpha of solvent molecules, you will find again an expression for the entropy of mixing, but this has more delicate, let's say, definitions in the sense that the solvation, so the binding of solvent molecules in solvation shell, is implicitly incorporated in the definition of the mole fraction Y alpha. So it's not that all particles which are in the electrolyte do contribute to the entropy of mixings, but only the ones which are free to permute. And that's the reason why you will find in the denominator of the Y alpha definition actually the solvation number. In accordance to that, for the mechanical part of the free energy density, which is derived from the idea that a certain amount of volume of the mixture is determined by the number of species you have at a given point in space times its partial molar volume. The partial molar volume is this V, the small v alpha to the v alpha r is for reference. So v alpha is the partial molar volume of a species. And again, here comes the solvation effect in play, because solvent molecules tend to have a far smaller partial molar volume than solvated ions. And you can account for this in a relation, in a simple relation between where pressure and let's say the volume your mixture requires. So this would be for a linear compressible material with solvation effects. You'll find this relation for pressure, and then you can more or less integrate this in a special way to obtain the mechanical free energy distribution. Now you can say, well, okay, is it really meaningful to consider a liquid electrolyte as a linear elastic material? And of course, this is not. Anyhow, we want to study in the next slides the incompressible limit. But what you can also do is you can use other mechanical relations. So for instance, in water, so water is slightly compressible. You have the so-called Tate equation of state, where pressure is related to volume by this polynomial representation here. And even for this, you can again compute a mechanical free energy contribution. And anyhow, this just should show you that this is really kind of, let's say, a framework type of model. So if you have a liquid which is more compressible than another one, then you would maybe have to use another state equation for the mechanical free energy density. In the incompressible limit, which really entails pressure as a so-called variable, you then find a more or less simple relationship for the chemical potential mu alpha, which is this psi alpha ref. That's a constant part. This is the chemical potential of the pure substance, plus kT ln y alpha. This is the entropic part of the chemical potential, or of the underlying free energy density, plus V alpha times pressure. And that's the mechanical part of the free energy density. And in accordance with the incompressible limit k to infinity, you get what is called an incompressibility constraint, which tells you that exactly this, that you cannot compress a given amount of volume. And this is reflected in a density way as the sum over V alpha partial molar volume times Y alpha is 1 over the total number of species you have. And let me point this out here again. So the impact of solvation is here in multiple ways. So entropically, via the definition of Y alpha, the mole fraction, and mechanically via the partial molar volume, which is in green here now, shown in front of the pressure term and also in terms of the incompressibility constraint. And well, this is nice, okay, but what you can actually do with it now, and this is what I want to show you next. So we consider now a metal electrolyte interface in thermodynamic equilibrium, so which means that you have diffusional equilibrium, so the gradient of the electrochemical potential is 0. You can integrate this. Then you have electrical equilibrium, so basically the Poisson equation, where the charge density Q is given as, the sum over charge number times elementary charge times the molar concentration of ionic species. You have mechanical equilibrium, so the gradient of pressure is equal to the Lorentz force Q times electric field, or gradient phi. And you have this thermodynamic closure relations, how the chemical potential is expressed in Y alpha and pressure, and the equation below tells you how Y alpha and N is correlated. And this is a rather general model framework for various salts, solvents, surfaces, and so on. And I want to show you in the next few slides how you can validate such a model. So first of all, we need to a little bit work out what is the what do we get out of the this diffusional equilibrium. So what is in the end the equation which has to be solved, or equations. So from the diffusional equilibrium, you can rewrite the mole fraction as a function of electrostatic potential and pressure. And inserting this in the representation of the charge density, you really get an explicit function of how the charge density Q, so the right-hand side of the Poisson equation, depends on electrostatic potential and on pressure. It's very important that it's dependent on both of these quantities, because the pressure term actually accounts for the size of the specific species. And another consequence is that with the Poisson equation and the momentum balance actually do not decouple, but they remain coupled. And now a very interesting quantity in order to validate this model is the so-called differential capacity. What is this? If you have a metal electrolyte interface and you apply a certain current, then you can measure over time how much charge has been flown. You can measure this charge, and from a theoretical point of view, this interfacial charge has contributions from the space charge layer. So here given in red. So that's the QE part, the volume integral or the line integral over Q in x direction, plus a surface charge QSE. And the capacity is then the derivative of this interfacial charge with respect to applied voltage. And this is something which can be very precisely measured and also be computed from a continuum thermoelectrodynamics. And based on the constitutive chemical potential functions I just showed you before, we can compute the capacity for different, salt concentrations, applied voltages, and so on. And this is what we are going to do next. Maybe an interesting aspect for people which are already familiar with electrolyte models here is, let's say, I used to call this the hierarchy of approximations. So a very, let's say, well discussed and investigated approximation or representation of the charge density is so-called Poisson-Boltzmann approach, where you write the charge density in terms of exponentials of electrostatic potential, and when you linearize this exponential function, you get what is sometimes called a Guy-Chapman approximation. And for these two approximations, you will find that the charge and the capacity, so the capacity becomes a constant in the Guy-Chapman approximation, or the interfacial charge a linear function, while for Poisson-Boltzmann you have for the capacity an unbounded cosine hyperbolic function, and both of these representations do have shortcomings with respect to the experimental data we find. So first of all, of course, if the capacity is unbound, this doesn't make physical sense. And on the other hand, capacity is not a constant in electrochemical systems. So both of these approximations do really have shortcomings. An ideal mixture approximation would be one where we would assume that all particles tend to have the same partial molar volume. If you do so, you already find these more or less well-known camel-shaped curves of the capacity. However, they still overestimate experimental data or experimental values by a factor of 10 almost. And if you now consider what we used to call a solvation mixture, where the Poisson equation and momentum balance do not couple, you finally get the capacity value into a realistic setup, which is in accordance to experimental data. The validation is performed here in the first place against a silver single crystal electrode. So it's really an atomically flat silver 111 surface with KPF6 in water, ultra pure water. And there's a variation of the salt concentration from 0.1 mole down to 0.025 mole. And you find that the capacity really depends nonlinearly on the applied voltage. And below you can see what the model I just showed you before is able to predict in terms of differential capacitance. So we have a qualitative agreement in the 1 volt potential range. You get quantitative agreement with respect to absolute values of the differential capacity, and also simultaneously with respect to salt concentration without any parameter adjustment. And this is a self-consistent prediction of capacity data sets based on this continuum model framework. Yeah, and one remark here, also for people who are already maybe a little bit more familiar with this, capacity itself is not a single equation, but an algebraic equation system. You basically have to solve two equations in order to get the representations I just showed you. This originates from the fact that also on PDE level, the Poisson equation and the momentum balance do not decouple. And then as in terms of their root functions, the capacity and this G function, they are not explicitly solvable. But numerically, you can, of course, just straightforward solve them. Yeah. And then another interesting aspect, which is maybe also related to people from DFT, is that in our derivation, we can actually show that this UM, so the quantity which actually enters as a voltage, is the applied voltage minus a constant, and this constant basically depends on the surface chemical potential of electrons, or another wording for this would be the work function. Yeah? And this is important because, as we'll see in a second, the surface chemical potential of electrons is dependent on the specific metal surface orientation. So for a 100 surface, you will have a different value as for a 111 surface. And for work functions, this is well known. And also for differential capacitances, this is more or less, or this is well known in the sense that the value at which the capacity minimum arises changes with respect to the metal surface orientation. Yeah? So for silver 111, you would have a different value of at where the capacity has its minimum compared to silver 110, for instance. And this is self-consistently also incorporated in this, or can be self-consistently incorporated in a non-equilibrium thermodynamic model, where the quantity of interest there is then the surface chemical potential of electrons. Another nice thing, what you can now do with all of this is you can actually compute the structure of the double layer. So we have actually used a PDE system in order to derive quantities, macroscopic or global quantities, the differential capacity, which has just integral terms within. And now we can use this validated model and compute backwards by solving the underlying PDE system how the structure of the double layer looks like. And what you will see here is on the left, you will have we will apply a voltage, and on the right you will have bulk concentration, and in the low potential regime, which is plus minus 60 millivolts, you will find that the electrostatic potential is just linearly or exponentially decreasing, and after a certain threshold value, which actually corresponds exactly to the maximum of the capacity, you will find an inflection point in space. And this inflection point in space gives you the opportunity to implicitly define something which is called Stern layer. This Stern layer, there's a Hilbert definition of Stern layer, where counter and co-ions immediately have a contact with the surface and say to form a Stern layer. And we can actually now, or we provided already quite some years ago, a mathematically sound definition of the Stern layer. So this is exactly the domain where the charge density has, for the first time, an inflection point. And you now can really compute, for instance, also the Stern layer width, so the thickness of the Stern layer as a function of the applied voltage. And you can also compute, for instance, the potential drop across the Stern layer also with respect to applied voltage. If you increase then voltage further, so this is the black line, so you're increasing voltage further and further, you see that the blue curve, this is, for instance, here the fluoride ion concentration, tends to saturate. And now something interesting also happens. Imagine these are solvated ions. They tend to have a really large solvation shell, and they require space. And because they do require space, they actually pump out solvent molecules into the other direction. And that's the reason why here this gray solvent concentration, which was originally in the order of 50, really decreases to values below one mole, meaning that the entire interface before the electrode surface is almost entirely filled with solvated ions. There are some solvent molecules left, but the main contribution here is solvated ions. And this picture here really corresponds to the branch, let's say, right to the capacity maximum. If you will go from the left maximum towards minus infinity, you will find the image just twisted. Then you will have cations here. Yeah, and now for this I mean this is then just it's just wording, but if you would call then from the surface to the inflection point, you can call this Stern layer, and from the inflection point towards the counter electrode, you will have a diffuse layer. And you will have really a locally saturated solution of anions here, which are the origin of the capacity maximum. Well, maybe some consequences I want to discuss here. So the capacity maximum is, and this can be proven mathematically, the capacity maxima are actually proportional to the partial molar volume of the anion, the solvated anion and cation respectively. So the left hump, the left maximum, is encoded by the molar volume of the solvated cation, the right one of the solvated anion. And interestingly, if you find, so there are several data sets which suggest that monovalent cations and anions really do have the same partial molar volumes. So maybe slight differences, but in general, they have almost the same value. The solvated ones, not the bare ions. Yeah? And a question, and I asked this myself for quite a long time, if this does also apply to other solvents as well, because everything I just told you yet was for water. And I got a colleague from electrochemistry in Germany, Helmut Balterstadt, into this, and he really made experiments on different solvents, so not only water, but here this whole series of water, PC, DMSO, acetonitrile, and declime, all for the very same salt KPF6, in order to test whether this hypothesis that monovalent ions have similar molar volumes does hold true or not, and also to let's say to provide data sets for model validation. So this is the next thing we wanna do. So everything we use the very same model framework I just told you, but not applied to water, but to different solvents, yeah, in terms of their different molar volumes V0 and dielectric constants, and see whether what we will find out. So on the left side, you see experimental data sets for KPF6 against a gold electrode. Gold is sometimes a little bit more tricky, but against gold. And on the right-hand side here is, let's say, what you would get out of this model framework by considering, again, solvation effects and the different dielectric constants the different solutes actually have. And it's really remarkable that you can achieve such an agreement. And if you now look into this line of solvated ions, we actually find that the capacity maxima, and they are weighted with the dielectric constant, so it's not one-to-one map, but you can recompute the partial molar volumes of the solvated anions cations in the different solvents, and it does look like as if they really have almost the same size among different solvents, even though they are very different in the sense that you can have very different solvation numbers. For instance, if you have a solvated anion with water, then you can have, let's say, for instance, 30 water molecules in 2 solvation shells. However, for decline, you will find a value of, for instance, 4 or 5 solvent molecules. However, the size of the solvated ions tend to be more or less the same, which is a bit of surprising. But on the other hand, electrostatic interactions do not care too much about the actual, or it seems like if they do not care too much about the actual chemistry, but more the steric effects because of the size of the solvent molecules. Okay, and another branch now towards, let's say, model validation. As I just said, there's this data set of Valette for KPF6 with water, and this is now more or less or was completed by Helmut and co-workers towards, again, other solvents, which are of course important for, I don't know, for batteries, for any other types of electrochemical systems. So this is despite its being important for fundamental research, they also have broad applications. So here, top right is the differential capacity for silver 111 with PC. Top on the lower right for acetonitrile, and then lower left for D-glyme, and upper left for DMSO. And they're not so perfectly symmetric because it's not really easy to have ultra pure unorganic solvents. So there's still a little bit debate whether let's say this tilted humps are due to experimental artifacts or if they are reality. But in principle, the trend remains the same as for water. So increasing salt concentration at a certain point yields that the minima becomes a maximum. You will find that the voltage values at the capacity values for plus minus infinity run to a constant independent of salt concentration. And we can do model validation in terms of trying to find, let's say, the set of parameters for the different solvents which actually produce the differential capacity curves and thus validate, again, the model framework. This is yet ongoing work, but we, in the first place, already found a pretty well agreement among the different solvents. And I mean, to be clear here again, this is all of the same set of equations, and the only quantity which is adapted is really the solvation number for the different solvents. So just as a remark here, this is more or less what you see on this slide here is the core of the underlying PDE system. This pi in front of epsilon 0 is the dielectric constant for the different solvents, and the main quantity which is tuned is really just the partial molar volume V alpha of the solvated ion in the different solvent molecules. One question which then comes up is, what is the actual relationship between partial molar volume and solvation number? So because mass, for instance, is conserved upon solvation. If I give you a sodium chloride and a certain amount of water molecule, and you put sodium chloride in this water, then the mass of both entities before and later on of the mixture remains the same. But volume is not necessarily conserved upon solvation effect. So solvated ions can have what I used to call pi alpha, a packing density. So for instance, how does really a certain amount of spheres pack into another sphere? And basically, there are this question arises in various ways. Yeah? So the packing of spheres into another spheres, and you can get packing densities from, let's say, stochastic algorithms of how you can pack. Yeah? So what is the packing density of 20 spheres into a larger sphere? So this is what you see here on the right, and yeah, this is let's say trying to get into the direction of relating the molar volume and the solvation number. You can also provide, let's say, structure models. So for the first solvation shell, these structure models are pretty well known because you can get them with XPS. But for the second shell, it's a little bit more complicated. But nevertheless, from structure models, you can again get something which is called, which you maybe call a packing density. So for instance, for the structure model down here, you will find that the solvation number of in total 24, so 6 in the first shell, 18 in the second shell, would lead to a partial molar volume which is 48 times that of the bare solvent. So here again, you can see that it's not a one-to-one map, molar volume and solvation shell, but they do have something to do with each other. Another thing you can learn from capacity measurements is, surprisingly, which I hopefully can convince you on the next few slides. And for this, we consider higher concentration. So you see here the capacity curves of DMSO, and you increase where the concentration is increased from 0.005 towards 0.1 mole. And if we put more salt in, then basically nothing happens anymore. So the curve remains the same. So the finding is that beyond a certain concentration, the capacity becomes more or less independent of additional salt you put in. And this doesn't hold only for DMSO, but also for instance, for calcium diperchlorate in water, for sodium diperchlorate in decline. So that's a rather general thing. And one way in order to understand this is that you consider incomplete dissociation due to solvation effects. So if you consider, for instance, a 1 molar solution of some ion pair AC, the common assumption of complete dissociation it can be questioned. So, for instance, if you look now into a space charge layer, you can see that actually the saturated layer of solvated anions is in the order of 1 mole per liter. So the local saturation is 1 mole. And if you have local saturation here, then you can also imagine that you would have bulk saturation also at about 0.5 molar of bare salt you put in, because then you would have 1 mole of anions, and so 0.5 mole AC gives you in total 1 mole of charged species. And if every ion agglomerates an amount kappa solvent molecules, then you will find that not enough solvent molecules are in the end left over. And by thus you have to re-question whether complete dissociation is always possible. And the way to do is that you rethink what is actually happening when you put a salt into water. So ACR, that's the bare salt, the solid, and you put this into water. Then it first dissolutes as an ion pair AC into solution, and then in a second step, it it takes over kappa A plus kappa C solvent molecules in order to form a solvated anion, A minus, and a solvated cation, K, C plus. However, if not enough solvent is left over anymore, then an ion pair AC simply cannot dissociate into anions and cations anymore. And this can be computed by the thermodynamic equilibrium condition here. So the chemical potential of the ion pair plus the chemical potential of solvent weighted with the solvation number kappa A plus kappa C has to be equal to the chemical potential mu A of the solvated anion plus the chemical potential of the solvated cation. And these are the very same chemical potential functions as we have used before in order to compute the double layer capacity. If you do so, you find that, and then you can introduce something which is called dissociation degree. This is quite well known from acids. Yeah? So the dissociation degree just tells you, the dissociation degree delta tells you how much of the solvent is dissociated into anions Na and cations Nc, and how much remains as ion pair NaC. And the thermodynamic equilibrium condition gives you this equation here. And the common equation in order to ask this question about dissociation degree is called Ostwald's dilution law. And if you compare these two results, or these two equations, then you basically find that whenever solvation effects do not play a role at all, then you get back to Ostwald's dilution law. However, and this is nice to see this in a comparison. So in an electrochemistry textbook, on the very first pages, you get said that strong electrolytes always completely dissociate, and for strong electrolytes, you would have large delta G of the dissociation reaction. However, in solvation mixtures, you will find that independent of the delta G of the actual dissociation reaction, after a certain concentration, the dissociation degree becomes less than 1, simply because not enough solvent molecules are left anymore in order for the ion pair to dissociate into solvated anions and cations. So beyond a certain concentration, and now this loops back towards the differential capacity, because now you can see that beyond a certain concentration, the actually capacity becomes independent of C, and you can actually compute this. So here on the top right, you see the capacity at the potential of zero charge with respect to salt concentration, and this really saturates after or beyond a certain salt concentration. And surprisingly, you can estimate the dissociation degree, or the Cmax, from capacity measurements, or use it implicitly in order to determine solvation numbers. Okay, so this all of what I have said was mainly for ions which do not what is called specifically adsorb on a surface. And the perchlorate here, sodium perchlorate, for instance, is an example set where the perchlorate ion as slightly adsorbs on the surface, and this can again be also achieved within this framework by introducing adsorbates which have surface solvation shells in a sense, yeah, or partially solvated ions on surfaces. There are different wordings for this. Mathematically, what happens is that you have an additional condition here, the adsorption equilibrium. So the amount of species on the surface is self-consistently also determined by the applied voltage. And you have thermodynamic closure relations. So here this mu S alpha is in a Langmuir type way is the surface chemical potential of some adsorbate on a surface which has a constant number of adsorption sites, and this omega alpha term here is the number of adsorption sites a partially solvated ion on a surface requires. And this loops back to a contribution of surface charge here, QSE. This is the amount of adsorbed charge on the surface due to these guys. And they do have also a surface capacity contribution. And this is really the origin why you can have unsymmetric capacity humps, where the right one, or this hump, actually comes from here, in that sense, adsorbate of perchlorate. And this also does hold true among different solvents. Here again, a series for not only for water, but also for acetonitrile, declime, DMSO. And you always find that one of the perchlorate, so the right hump, is elaborated compared to the left one, which is reflected for sodium. And here the validation process is still a work in progress, but the trend is again quite similar. The last question I want to point out here is the discussion of multivalent ions. So right now we were talking about mainly monovalent ions, but we all know that, for instance, in bioelectrochemistry, calcium is a main player. So and in order to provide also models for instance, I have projects on ion channels for where calcium ions can flow through. We want to understand how the partial molar volume and the solvation number, how do they interact, or how are they dependent on the charge number set of the specific ion. And the good thing is we can state 3 different models for this. So in first one, M1, is where we assume the solvation number is independent of charge number. The model M2 is where the solvation number scales linearly with charge number, and M3 is where solvation number scales quadratically with charge number. And for these 3 models, we can again compute the differential capacity, and you see here the respective curves. So the dashed ones are M1, the filled one is M2, and this dashed dotted one is M3. And there is a series of measured data, rather rough or crude data from Graham. This is already from the 50s or 60s, I guess. So not too much reliable, but he already introduced the idea that here in this sense, chloride, so the anion always remains the same, but the cation changes its valency. So from cesium and sodium monovalent to magnesium barium having a charge number of 2, and aluminium lanthanum having a charge number of 3. And these data sets already suggests that the solvation number scales really with linearly with charge number. However, this is not too reliable, this experimental data set, and so I asked again here my colleague Helmut Baltuschat if he could provide more data sets for this. And here is, let's say, the first more or less tried to complete these data sets. So you see on the top row sodium perchlorate in 3 different solvents, and in the second row calcium diperchlorate in different solvents. So in the top one you have monovalent ion sodium, and on the lower row you have a twice valent cation calcium. And you find again that the capacity value for very negative potential values remains to be equal among the different solvents. And this again, he really suggests that solvation number scales linearly with charge number, which did surprise me in the first place a bit, because I assumed maybe that there is a square happening, but it doesn't seem to be the case. There are experiments going on right now also on 3-valent ions in order to complete this data sets, but that's so far the understanding we have. So I have a couple more minutes where I want to show you what comes next once or what you can actually now do with this. And a nice, let's say, straightforward, also mathematically nice extension is towards polycrystalline electrodes. So everything I have told you until now was for metal electrodes, which are really atomically single crystal electrodes. And now we wanna discuss an electrode which consists of various facets here in colored, which you just label by indexes I, and we can apply a global voltage E of this polycrystalline metal surface with respect to some electrolyte, and do again the same thing. So we can store charge, we can define a capacity for this polycrystalline interface, and the nice thing is that, or what means nice, we actually find that there are then two scaling parameters. So the first one is the width of the Debye layer or of the space charge layer, and the second one is the diameter or the size of the facets. So these are the two competing quantities here. And at every facet, you will find space charge layers computed from the very same model, which I have just showed you before. And this introduces the Debye length. And here on the top right, you see what introduces the facet size. And yeah, let me point out what results we can find. So M1 here means whenever the facet size is large compared to the Debye length, then you find what is here on the right side written. So the C poly, so the differential capacity of a polycrystalline surface, is the sum over all facets where the capacity function of the individual facets comes into play, and weighted with SI, that's the area of the facet with respect to the total area. And the main important point here is also that in the argument of this function CPL hat, there is this surface chemical potential of electrons, mu SE to the index I, which is the work function of the electron for the different surface facets. And for instance, for a bicrystalline surface, it's not so easy to be seen, but consider you have a metal surface which consists of two facets. Then you will find the magenta lined capacity curve as the one for a polycrystalline or for a bicrystalline surface. We can even do this more also spatially resolved for 2D and 3D examples. So on the lower left, you will see the space charge layers for a two-dimensional polycrystalline electrode. And there you can already see that even at an applied voltage of 0, you can have facets where you have a positive space charge layer, and you can have facets where you have a negative space charge layer, while globally you would remain being electroneutral. And then the corresponding capacity functions with respect to applied voltage can, of course, be even more complex, as shown here in the center part. Now, labeling the facets just by numbers is not the smartest way you can actually do. There's a far more elegant way to label these, and this is by using the work function itself as an indicator function for the different facets, because this is what you would also measure with STM. And if you do so, you can introduce a distribution of surface fractions and get a stochastic description of polycrystalline surfaces. And there we can really prove that you, in the end, obtain this nice convolution equation for the differential capacity of a polycrystalline surface. So it's the distribution function f gamma, f omega of surface facets with respect to work function convoluted with the boundary layer capacity of a single crystal electrode. And here is now an example. So on the top right, you see this distribution function starting from a delta peak, and it's getting broader just over let's say the parameter study I will show you. So once this distribution function broadens, you can also see how the differential capacity of the polycrystalline surface smears out to become just this hump and become even more and more flat. And that's the main reason why for polycrystalline supercaps, for instance, you don't see any capacity humps at all anymore, but just, let's say, this single humps which you see down here on the right-hand side. So that's the conclusion here. We can also prove what is happening when the facet size becomes very small compared to the debye length. Then you get another limiting equation system for the polycrystalline differential capacity and potential of zero charge. But that's kind of, let's say, details, which I'm happy to answer while I'm in LA. And this is, in my opinion, really crucial for a better understanding of the nanometer scale electrocatalysis and what is really going on in these types of systems. And I think this is a good point to stop here for today, because then the next branch in part 2 will then cover also what is happening when the dielectric constant is not becoming a constant anymore, but field and concentration dependent.